Now, to solve equations like this, we basically have three options. The first option is we could set these two equal and then type it into Wolfram alpha and see if it tells us anything useful. It turns out, though, that this is one of these nasty transcendental equations that does not have a known solution in closed form. Now, you never know with Wolfram alpha. It might find a solution for you in terms of some very obscure hypergeometric function, but that solution isn't going to be particularly useful. For example, ultimately, we're going to need numbers if we're going to try to design, say, the energy levels in this quantum well laser. And also, just knowing it in terms of some obscure function really doesn't help us build up much intuition about the system and how it's behaving. The second type of an approach is you can set these two equal to each other and write some computer algorithm to solve that equation and then get out at least numerical values. That would be useful for some kind of engineering design, but it doesn't really provide much insight. So we are actually going to go with the third type of option. It's somewhat of a lost art, but it is the graphical solution. And one of the beauties of the graphical solution is that by visualizing what is going on as you solve an equation like this, it can actually tell you some things that would be very hard to know for sure when you're looking at some obscure hypergeometric function or when you're just looking at a set of numerical values that came out for some specific case that you had calculated. So we're going to work towards doing this as a graphical solution. So the way that a graphical solution works is that when I want to equate two things, like this cotangent with this function over here, or likewise this tangent and equate it with this function over here, we simply graph both functions. So I'm going to make a plot then of how these functions behave as a function. I'm going to try to make this more of a straight line, right? That's better, right? As a function of wave vector k. And then, whenever the two functions are equal, we will have a crossing between two different curves, something like this cotangent curve and this unusual k over alpha curve. And wherever those two happen to cross, we know then that's where we would be looking at actually a solution to our equations. Now, to do this, let's start by plotting. So we have to plot both the type 1 and type 2. I'd like to begin actually by plotting the type 2 tangent function because tangent's a little bit more familiar to us. So let's start then plotting the tangent function. So we have minus tan of Ka. Now we know tangent behaves linearly near the origin. So this thing is going to, but I have a minus sign in front, so it's going to have some downward slope, maybe something like so. Maybe a little bit less slope. I'll try to sketch it something like this. And then as I move along, right, tangent will keep increasing. But tangent does something very interesting, right? It eventually blows up and it goes to infinity at a certain value. And where the tangent goes to infinity, that is at pi over 2. So that asymptote that I'm going to hit, it's going to look something more or less like this. Here, maybe I'll make it come in with a little less slope here, right? And then have them asymptote like so, like that. That's pretty nice. That asymptote value is pi over 2, but I'm going to write it as pi over 2a because remember, I take k, I multiply by a, and then I'll be taking tan of pi over 2. It will go down to minus infinity. Now, I hope you also remember that the tangent function has these different branches. So when I cross over its asymptote, what it does is it goes to infinity on the other side, but with the opposite sign. So it's actually now going to be coming down from infinity. And it's going to come down from infinity, and it eventually crosses 0 again. And the value where tangent crosses 0 is actually equally spaced. That happens at pi. So let me draw in another dashed line, equally spaced. So this will then be pi over a. And that's where my function will come down from infinity. It will cross, sorry for the jaggedy curve here, down from infinity, cross through my axis, and it's going to diverge again. And it will diverge again at now an odd half pi. So that will happen at 3 pi over 2a. And that will come down like so. And let me draw maybe just 2 more of these. Here will be another one, right? Where I will be coming down from infinity. I will cross 0 at 2 pi over a, which somewhat completes my cycle, like so. And then I will eventually even out here at 2.5 or 5 halves. So 5 pi over 2a. That's where I'm going to have now another asymptote. So what I've managed to chart for you here so far is minus the tangent of k times a. That's the tangent function. Let's now turn to the cotangent.